Alright, ladies and gents, welcome back. We're in the next section, 9.4, direct comparison test. So what we want to do is we want to use the direct comparison test to determine convergence. So we've talked about some convergence tests so far. We've talked about the nth term convergence test, the geometric, the integral test, and the p-series test. But they've been fairly simple, right? And they have pretty special characteristics that if we use the characteristics for each of those tests, like, we can find convergence very easy. But what happens if there's any slight deviation from those characteristics? Okay, we don't really know what to do yet. And if there's any slight deviation there, we can yield a series where we don't know how to do that. And so, for instance, 1 over 2 to the n is geometric. So we talked about that, geometric test, one of the first videos in this section. But if I change the 1 to an n, this is not geometric. Okay? So we can't use the geometric test because that's not geometric. Number 2, so this is the p-series test from the last video. And if I add a 1 to the bottom, that's no longer a p-series anymore. So we can't use the p-series test. And then if I have some series here, some sequence, n over n squared plus 3 squared, this is pretty easily integrated, right? I could make n squared plus 3 my u, and then I can integrate that, and the n's cancel, and that's pretty easy. But if I took this, n squared over n squared plus 3 squared, this is not easily integrated. Like, we can do this by integration by parts. Actually, we might be, well, we can't use trig. Maybe we can use partial fraction decomposition, but we could do this, but it's not easily integrated. And so what we're going to do today is we're going to do this thing called the direct comparison test. And what does it do? Well, it basically says that we can determine the convergence for complicated positive series by comparing them with simpler series. Okay, so some easier ones. So basically this is what the direct comparison test says. That if I have some series and it's between 0, so this is between 0 and some series, if I can find another series in between those two series, 0 and whatever b sub n is, then it's going to converge to the same thing. So it's going to converge. I don't care what the value is, I guess. I don't care what it converges to, but it's going to converge. So if b sub n converges, right, then a sub n converges because a is in the middle of 0 and b. If a sub n diverges, okay, so if some function here, a sub n diverges, then b sub n also diverges, okay? So this is going to be true, all right? Now, you cannot say if b sub n diverges, so if this was a b, then you cannot say a sub n diverges because it could diverge or converge. So it could be one or the other. So that, like, contrapositive piece or contradiction or whatever, like the backwards, doesn't work, okay? That doesn't imply, so b sub n diverges does not imply a sub n diverging. Let's get into some examples. So I want to determine, okay, if these functions or if these series here converge or diverge. So what I want to do is I want to take the series, sequence, all this stuff here, summation, and I want to compare it to some crazy function. Well, which function expression can I actually compare this fraction to? Well, I'm going to compare it to 1 over 3 to the n. Because if I think about it, this really 2, it doesn't do much when I have 3 to the n power. That 2 doesn't do anything, right? 3 to the 100 plus 2 doesn't really do much. So I'm going to compare it to that. So we can see that 1 over 3 to the n is actually going to be bigger than 1 over 2 plus 3 to the n. And some of you are like, well, what do you mean bigger? I don't understand bigger. Like, if n was 2, okay, we'll make n 2. That means this is 1 over 9. This is 1 over 11. Well, this fraction's actually bigger. Like, the quantity of that fraction, this is 0.0111 repeated, and this is 0.0999 repeated. Well, 0.01, it's 0.11, sorry. 0.11 repeated is bigger than 0.09 repeated. So that's why this fraction's bigger. Okay, so that's why I can say that 1 over 3 to the n is bigger than 1 over 2 plus 3 to the n. Then we can say, okay, now if I take another summation of this 1 over 3 to the n from n equals 1 to infinity, we know this here is going to converge because of the geometric test when r is less than 1. Okay, r is less than 1. Again, that's from a couple videos ago when we talked about geometric tests. You got to go back if you forgot what r is less than 1 stands for. Okay, so then, therefore, we can say that the integral, or the summation here of the original series, 2 plus 3 to the n from n equals 1 to infinity, also converges by direct comparison. Okay? So because we found another function that mimics this function here, it mimics it, because that converges based on the geometric test, because r is less than 1. I'll put this around parentheses. Okay? Because the geometric test, I guess I didn't put test. Alright? And because it mimics that, we can say that because 1 over 3 to the n mimics this, and this converges, this is going to imply that this one is going to converge. Okay? Let's go to the next one. You can see that I had to change n equals 1 to n equals 5. I'll explain why I had to do that, so make sure you do that on your paper as well. So anyway, I have that summation of 1 over root n minus 2, and I'm going to take this negative 2, and really it's negligible, so that doesn't really matter. And so I'm going to compare this to 1 over root n. And again, that negative 2, like at infinity, that doesn't really matter too much. And so I'm going to compare 1 over root n. And I'm going to say that 1 over root n is actually less than 1 over root n minus 2. And again, we kind of worked on this over here, and how do we understand that it's greater than or less than? Well, at 5, and so I'm at 5 right here, okay? This is 1 over the square root of 5, which we're going to say this is a question mark, because we don't know if it's less than or not. So this is 1 over root 5 minus 2. But what is 1 over root 5? That's about 1 over 2.41. Okay, and we don't know if it's actually less than. This here is 1 over root 5 minus 2, so 2.41 minus 2 is about 0.41. Well, hopefully, you know, you're in Calc 2 for a reason, and you can see that this is actually going to be a bigger number than this. This is not quite a half. This is a little bit less than a half. This is going to be, you know, somewhere in the 2 range, 2.5 or so. Okay, so that's why it's bigger. Okay, and it would continue being bigger all the way up through infinity. So this is not a question mark anymore. This is serious. This is bigger than the left side. Okay, so I'm going to get rid of this so we can work on some calculus. Okay, so I want to compare this function. This is my new function. So from n equals 5 to infinity of 1 over root n. Well, this is going to diverge. From the last video, it's going to diverge because of the p-series test. Because of p-series test. Okay, because p is equal to a half, right? And therefore, that's less than or equal to 1. And so because p is equal to a half, which is less than or equal to 1, this is going to diverge. Thus, okay, our original n equals 5 to infinity of 1 over the square root of n minus 2 is going to diverge by direct comparison. Direct comparison. Okay, let's move on. Alright, let's go to the last one here. We have the summation n equals 1 to infinity of 1 over 4 times the third root of n minus 1. Now, I'm going to find a comparison. So my comparison that I'm going to use is 1 over n. And you're going to be like, wait, why? Why am I going to compare it to 1 over n? Well, here's the reason. So we can see that this is really n to the 1/3, right, times 4, and then minus 1. The minus 1 is negligible, So that doesn't really matter too much. And the 4, honestly, is pretty negligible as well. When I'm approaching infinity, this is going to be infinity to the 1/3, which is actually still going to be infinity, right? So 4 times infinity is still infinity. Minus 1, that's still technically infinity, if you think about it. And so those are all negligible terms. And because the variable n is really the only thing that matters, that actually grows, or in this case it's actually going to get smaller because it's 1 over that. So this is actually going to probably, if we took the limit of this would go to 0, right? But I'm not taking the limit of it. But anyway, so I'm going to compare it to 1 over n. Now, could I have easily compared it to n to the 1/3? Well, yeah, sure. I mean, yes, that makes sense, but, you know, I want to just give it a little bit more shot so understand why I can do this. If we remember the p-series test, the power, right? If the p-series, if that power, n to the p, is between 1 and 0, right, this is going to diverge. So even if you chose n to the 1/3, right, or n to the 1, like, it's still going to diverge by direct comparison, okay? You can't say, obviously, n to the 2 power, because that's definitely not the same, okay? So it doesn't really matter too much what you choose, as long as you're able to choose something that you know is, you know the value of, right? And so then we know that 1 over n is going to be less than 1 over 4 third root of n minus 1. So let's say n was 5. Just to make sure we compare this, okay, that we're actually on the right track. If this is less than or greater than, I don't know, we got to make sure. So 1 over 5 less than 1 over 4 times the cubed root of 5 is actually about 1.71 minus 1. So 1 over 5 is less than 1 over, this is about 6.8, so that's about 5.8. This here is not true. Not true. Okay, so what the heck is going on here? Well, what if we made n 7? Okay, let's say make n 7. So I get 1 over 7 is now less than 1 over 4 times the cubed root of 7, which is, I gotta do the math here, we get 1.91, okay, minus 1. 4 times 1.91 is about 7.65, give or take, minus 1. So that's 6.65. And that is now okay. This is now true. So this function, okay, is actually going to be smaller for n equals 1 to n equals 7, or n equals 5, 6 actually. Okay, I didn't do 6, but it's actually going to be, the left side is going to be bigger than the right side at n equals 6 as well. So on these pieces here, n equals 1 to n equals 6, the left side's actually going to be bigger. But after n equals 7, so n is greater than or equal to 7, the right side is going to be bigger. And so you're like, well, why does that work, or what happens here? So because this summation means we add up all of this stuff, okay, we're adding up, you know, when n is 1, we're adding that to n equals 2 and 3 and 4 and 5 and 6 and 7 and 8 and so on up to infinity, we can forget about finite terms. Forget about finite number of finite terms. Of, that's supposed to be an of. As they will not affect affect. I'm going to say affect. I don't know. I think affect is wrong. I think it's effect, but I don't really care. Whether the series converges or diverges. Okay? Because it's a finite number, meaning I can actually count to it, like it's a countable number. N equals 1 to n equals 5. Those are countable values. I could easily find those values out in the series here. Okay? But I don't really care about that. I care about infinity. And because infinity is a non-countable number, that's going to be crazy large, and I'm not ever going to reach it. If I can count to something, I can forget those values and just worry about where it matters. And it matters when n equals 7 and beyond, like Buzz Lightyear. Okay? So, now that I have your attention, okay, I can compare the 1 over n. Okay, we know that... Actually, it really didn't even matter in this problem, but it's fine. 1 over n. We know this is going to diverge because of the p-series test, right? Because p is equal to 1, which is less than or equal to 1. So, because of the p-series. So, we know that the actual original series, 1 over 4 third root of n minus 1, is going to diverge because of direct comparison. Okay? It doesn't necessarily matter what you choose as long as you can tell which is greater. So whenever you compare your new kind of series or your new fraction or your new function, whatever you want to call it, with the original, and you get a less than here, if that less than holds true, then you should get a diverging sequence or series. Okay, you should get a diverging series. If it doesn't hold true and it's actually greater than, like you had on the very first problem, let me scroll back up there, on this one here, because that was a greater than, 1 over 3 to the n is greater than 1 over 3 to the n plus 2, then this is where you're going to get a converging sequence. Okay, converging. I spelled it wrong, but that's okay. Alright, so just be aware of that. Make sure you're comparing correctly. Okay? But that's it for this video. Deuces.